Alright, so in this video I'm going to be showing how to use calculus to find the area of, to find the volume of a solid generated by revolving a function around the x-axis. So to start with, we know that an integral is the signed area underneath a curve. So here's just an example of that. You have a curve here, like y equals x squared here in blue, and then from the origin to this point here, the integral is just everything in red. It's the area underneath the curve. And it's important that you say it's the signed area because if you had negative x squared and the function turned down like this, the integral would actually be negative. And so that's an important distinction because you can't necessarily have negative area, but when we're talking about integrals, you have to also take into account the negative things. Okay, so then we also need to have sort of a fundamental understanding of what volume is, and that's just basically the amount of three-dimensional space that an object occupies. So here's a very simple example of that. You have a cube here, a rectangular prism, and the volume of that is just length times width times height. Pretty simple. But there's another way of thinking about volume, which is particularly useful when it comes to finding the volume of more abstract shapes. So what we have here is the same cube, and one way to find the volume of it would be, like I said, to multiply the length times the width times the height. But another way is you could slice it up into slices like this, and then you could find the volume of each of these slices and then just add it up. Which is, I mean, if you think about it, it's the same thing, but it's more useful if you have something that isn't exactly this shape. So you can think about this example as like a deck of cards. So you could find the area, or you could find the volume of the deck of cards by multiplying its length times its width times its height. Or you could find the volume of each one of the cards and then just add them all up. So what I'm talking about here, where it could be more useful, is if you're trying to find the volume of something like this. Sort of a parabolic shape, like maybe a vase or something like that. And here you can see it's very, I mean, you can't just take the length times the width times the height. It's not a cube, it's not a rectangular prism, it's not sort of a basic regular geometric shape. And so here, when you split it up, you see that all of these little slices are circles, which is important because if you can find the volume of each of these circles and then you add them up, then very easily you can find the volume of this shape here. And when the calculus comes into play here, when we create an infinite number of slices. So technically you can think of the height of each of these slices as being infinitely small, which sounds like using an integral. So to illustrate this, let's just go back here. We can think of something like what we're trying to do here is let's just talk about for a minute what it means to revolve a function around the x-axis. So we can draw our set of axes here. So we have y and x. And suppose we start with, I don't know, like y equals x squared, and I just draw the positive half of that. So when we want to find the volume of this, when we revolve it around the x-axis, what that means is that we're taking this line, and then we're adding a z-axis, sort of creating this three-dimensional space. And if I can kind of draw this here, you end up bringing it around, so you create a shape like this with an opening here at this end, if you can kind of see that. And you create sort of an open shape, and then this would be the x-axis, and you can sort of think about you're revolving it around. So if you take this line and you go all the way around the x-axis, you create a shape that looks kind of like this, sort of like a cone, right? And then, so this is all on the inside and here. And you just look at that, you can't find, you can't easily just find the volume of that by multiplying a few numbers. You need to use calculus. So to sort of explain the process of this, let's start with sort of a very basic example. So let's suppose that we have a function, let's say y equals 2, just to sort of show this. So again, we'll draw our axes like this. So y, x-axis. So here, this is 2. So if we draw the function y equals 2, and suppose we want to revolve this around the x-axis, alright? So what we'll end up having here is a cylinder, right? So when this goes all the way around, it'll end up here, right at the bottom, at -2, and then it'll come back up sort of out of the page to create a cylinder. And say we want to find the volume between 0 and 4. So we're going to end up having a cylinder like this, kind of like that. And just because this is such a simple example, you could say, alright, so we have a cylinder, you draw it again like this. Alright, we know that, okay, because this is y equals 2, so here this is 2, this is 4, so the radius is 2, then you can find the area of the base, and then multiply it by the height here, which is 4. Alright, so you can do that using geometry. But there's another, maybe perhaps more interesting way to do it, like I said, using an integral. So if you think about here, so we want to find the volume of this shape between 0 and 4. So those are sort of the limits, right? Y equals 2 extends forever, but we're just concerned with this little space here. So, like I said, the first step is sort of to visualize what it will look like when you revolve it around. So if you have a straight line and you revolve it around the x-axis, you end up with a cylinder like this. And then you need to sort of understand what that means. So first of all, you want to find out you just want to see what it looks like in three-dimensional space, so it'll help you sort of visualize it as you move on. Alright? Alright, so you have to find out what the shape looks like. And then sort of the second step here is to figure out what about this function can help you find the volume of this particular solid that we're interested in. So in order to do this, you should first know well, let's back up a little bit. With the method that I'm talking about here to find the volume of solids is called slicing. So in this particular solid, in a cylinder, if you cut slices through a cylinder like this, what you end up with is a bunch of circles, right? So a circle, it's just a stack of circles you can think of. And we know how to find the, volume of a circle. So if you created, if you could find out what the volume of all the circles was and you can add them up, then you would know what the volume of the cylinder is. But the problem is a circle doesn't have a volume, so you need to use the integral to make the circles infinitesimally thin, so that you can add them all together and they do create this solid. So let me show what I'm talking about here, kind of. So we know that, just from basic geometry, that the volume of a cylinder is equal to the base times the height. Okay? And that's also equivalent. We know the base is a circle, so that's pi times the radius squared times the height. Okay? And so, why don't we just find the volume of this thing using the using geometry we know. Alright, so the volume of this is okay, pi times 2 squared times 4, so that's 16 pi. Okay, that's the volume of this thing. Okay, so we found it, but that's not very interesting. We want to use the integral to find out what the shape looks like. And so the way we do this is we know here that sort of the limits of what we're interested in is 0 and 4. So let's just switch to a new page here. When we're writing an expression, an integral expression for finding volumes, so we're interested in the space between 0 and 4. And because we're using the slicing method, we want, so the function that we're interested in is the area of each of these slices. So a cylinder, right, as I talked about before, it's just a bunch of circles you can think of that are just sort of stacked together. And because we're slicing it up like this, what we're interested in, what's going to help us find the volume is the equation for the area of this circle. Okay? So that's what we're going to use in here as the integrand. So in this particular case, now we have to think about what is the area of each of these slices. We need to sort of rationalize that. Okay, so you can think about, alright, each of these slices, right, they're all going to be the same. They're all circles, they're all the same height because this is a cylinder, so the radius of each of them is going to be 2, okay? You can also think of that as saying the radius of each of these is going to be f of x, because regardless of where we are on the x-axis, the height, or the radius here, is going to be exactly 2. So, like I said earlier, f of 3 is 2, f of 1 is 2, f of 2 is 2. So, as sort of an equation for the area of each of these slices, so the area of the slice is equivalent to pi times f of x squared, right? That's going to be, if you think about, if we just draw on a slice here, okay? Like that. Here, right, it's a circle, so the radius is going to be f of x, pi r squared, so pi times the radius, which is f of x squared. So this is the area of a slice, okay? So this is the first important step. Now, this area of the slice goes into our integral expression here. So we're interested in the volume between 0 and 4 of the slice pi times f of x squared. So if we can sort of think about this expression in terms of the solid here, we're trying to find, if we take an infinite number of this area, the area of this slice, of this circle, if we take an infinite number of them and pack them in between 0 and 4, what's the volume, right? That's going to give us this. That's the same thing as finding the area of this base and then multiplying it by the height, right? This is the area of the base, this is the height between 0 and 4. And it's also important to write times dx, because this is the variable that we're doing. It's all the changes are with respect to x. The function is defined in terms of x. Alright? So, we've just written an expression for the volume of this solid of revolving f of x equals 2 around the x-axis to create a cylinder, and there's the integral expression. So earlier we found out that, just with geometry, what we already know, that the volume of this is 16 pi. So let's solve this integral expression and see if it is 16 pi. Let's see if this makes sense. Okay? So, we know from our fundamental theorem of calculus part 1 that well, even before that, just from our properties of integrals, we can, pi is a constant, so we can take that out in front. So pi times the integral of 0 to 4 of f of x squared, oops, dx, okay? That's the same thing. This is equal to the volume. Alright, so we know that f of x equals 2, right? This is the function we're concerned about, so we can just substitute in the function, right? If f of x was like 15x squared, we'd substitute that in. But f of x, in our case here, is 2, so we write pi 0 to 4 of 2 squared dx, alright? So that's the same thing as pi from 0 to 4 of 4 dx. So now, here's where we use the FTC part 1. So we find the antiderivative of the inside part, which is 4x, alright? So that's big F of x, that's the antiderivative. So this expression here is going to be equal to 4 times f of b minus f of a. Okay, that's just your FTC part 1. Okay, so that's 4 times, right, f of x is 4x, so that's going to be 4 times 4. Or no, sorry, why did I write 4 out here? Pi. This is pi, sorry. Alright, so 4 times 4 minus 4 times 0. Okay, sorry about that. So here, f of b minus f of a, that's your fundamental theorem, and then we just substitute that in. So what we get here is 16 pi. Alright, it's exactly what we got before. Okay, so at this point it may seem a little bit unflattering. Okay, fine, we can find the volume of this. We could have just used geometry. But I just use that as an example to sort of illustrate how to use integrals to do this. Alright, so now let's think about an example that is a little bit more useful here. Okay, so let's draw another function here. Let's draw, from the beginning, let's just draw x squared, okay? So here we have f of x equals x squared, okay? So, that's in blue. We should label our axes. This is y, this is x. Okay. So now, suppose we want to now take this function and revolve it around the x-axis. So the first step here is to sort of think about what that looks like. If we take this and revolve it around the x-axis, we're going to, let me just draw off to the side here, we're going to get a shape that kind of looks like this, kind of like the, like the bell of a trumpet or something, sort of a cone out like that, and then this would be the inside. Okay? So now, let's create a problem out of this. So let's say we'll use the same limits between 0 and 4. Okay? So we want to find the volume of the solid generated by revolving f of x equals x squared around the x-axis. Alright, so that's what it's going to look like. So this is the x-axis going through there. We want to find the volume of that. Say this is at 4. Okay? So, just like we did before, our limits of integration are between 0 and 4. Now, we want to find out what volume is of one of these slices, or sorry, what the area is of one of these slices. So you can write that as sort of like A. That's the area of the slice. Now, just like with the cylinder example that we used here, each slice is going to be a circle. But this time, not all the slices are going to be the same, right? If you take a slice here, it's going to be a circle, the radius is going to be 2, same thing here. But because this is a parabolic function, the circles here are going to be different in size, alright? So we can model this with our area function. So we'll write here, area is now f of x, again, squared times pi. So pi r squared, right? This is the area. Okay? But now, instead of having our function be explicitly defined, it's defined in terms of x. It's x squared. So that means the area is x to the 4th times pi. That's the area of one of these particular slices, okay? Now, from before, the step is to put the area of the slice in here as the integrand, right? So, pi times x to the 4th times dx. Okay? So now, this, very similar to our previous example, right? We found the area of the slice, pi times f of x squared. It's a circle. We've put that into the integrand. We have our limits of integration, right? We're revolving it around between 0 and 4. That's what we're interested in, this sort of cone solid we have here. And now we can find the volume. Okay? So this is a more useful application of this concept here. Because if you look at this shape, right? If you look at this shape, you can't find the volume of this just by using geometry, right? You can't just see, okay, length times width times height, or like for a cylinder, you can just remember, okay, it's the area of the base times the height. Here, you can't find the exact volume of this without using an integral, which is why this is very useful in finding certain shapes. Like, here I have an example. This football is something that you could find the volume of relatively easily using this same method, right? Think about it like this. Each of the slices is going to be a circle, right? So you need to find the equation of this parabolic line here, probably like an x squared function, and then, right, you'd find the area of the slices, and then you could relatively easily find the exact area of this football, which you wouldn't otherwise be able to do just by looking at it, right? So that's why this is useful, and I'm not going to go through and solve this because it's exactly the same, but I guess you'd use the fundamental theorem part 1, and you'd simplify this, and then you could be able to find the exact volume of this particular substance. So there's the video on finding definite volumes of functions being revolved around the x-axis. Thanks for watching.